Have you ever looked at a glowing piece of hot metal and wondered why it changes color from red to orange to white as it gets hotter? It seems simple, right? But at the end of the 19th century, this simple question was a giant headache for physicists. They tried to explain it using the rules they knew, what we now call classical physics, the laws of Newton, and Maxwell, that perfectly described everything from falling apples to the planets orbiting the sun. But when they applied these laws to the glow of a hot object, the math went haywire. Their theories predicted that any hot object should be blasting out an infinite amount of energy, especially in the ultraviolet range. This embarrassing failure was nicknamed the ultraviolet catastrophe, and it was a giant red flag that something was fundamentally wrong with our understanding of the universe. Physics was broken, and it was going to take a revolution to fix it. This is where a brilliant physicist named Max Planck enters the story. In the year 1900, wrestling with this very problem, Planck made a radical, almost desperate suggestion. He proposed that energy wasn't a continuous, smooth flow like water from a tap. Instead, he said, energy comes in tiny, discrete packets, like individual drops of water. He called these packets quanta. Imagine you're climbing a ramp versus climbing a set of stairs. Classical physics saw energy as the ramp you could be at any height. Planck's idea was that energy was like the stairs, you could only be on one step or the next, but never in between. The size of these energy steps, he figured, depended on the frequency of the light. It was a bizarre, counterintuitive idea that went against everything physicists believed at the time. Even Planck himself wasn't entirely convinced. He thought of it as just a mathematical trick to make his equations work. He had no idea that his trick had just laid the foundation for a whole new reality. He had accidentally opened a door to a world that was stranger and more wonderful than anyone could have imagined. 5 years later, in 1905, a young patent clerk named Albert Einstein took Planck's strange idea and ran with it. Einstein was tackling another puzzle of the time, the photoelectric effect. Scientists had noticed that when you shine light on a piece of metal, it can knock electrons loose. But here's the weird part. It didn't matter how bright the light was. A dim blue light could knock electrons out, while a super bright red light did nothing. According to classical physics, where light is a wave, a brighter light should have more energy and should have no problem ejecting electrons. It just didn't make sense. Einstein, in a stroke of genius, proposed that Planck's quanta weren't just a mathematical trick for hot objects. He suggested that light itself is made of these packets of energy, which he called photons. A photon of blue light simply has more energy than a photon of red light. So, it wasn't about the brightness or the number of photons hitting the metal. It was about whether each individual photon had enough of a punch to kick an electron out. This explained the photoelectric effect perfectly and proved that Planck's quanta were real, physical things. For this work, not for his more famous theory of relativity, Einstein would later win the Nobel Prize. The quantum revolution was now officially underway. With the reality of quanta established, the next target was the atom itself. The popular model of the atom at the time was like a tiny solar system, with electrons orbiting a central nucleus, much like planets orbit the sun. But there was a huge problem with this model, again thanks to classical physics. According to the established laws, an orbiting electron should constantly radiate energy, spiral inwards, and crash into the nucleus in a fraction of a second. If this were true, atoms couldn't exist, and neither could we. Everything should have collapsed long ago. The universe was stable, but the theory said it shouldn't be. In 1913, a Danish physicist named Niels Bohr came to the rescue. Inspired by Planck and Einstein, Bohr applied the quantum idea directly to the atom. He proposed that electrons couldn't orbit at just any distance from the nucleus. Instead, they were restricted to specific, allowed orbits, or energy levels, much like the steps on Planck's staircase. As long as an electron stayed in one of these special orbits, it wouldn't radiate energy and wouldn't spiral to its doom. It could only jump from one orbit to another by absorbing or emitting a specific quantum of energy, a photon. If it absorbed a photon with the right amount of energy, it would jump to a higher orbit. If it dropped to a lower orbit, it would emit a photon of a specific color. This model brilliantly explained why elements, when heated, emit light only at specific, characteristic colors. It was a major leap forward, marrying the quantum idea with the structure of matter itself. The work of Planck, Einstein, and Bohr marked the explosive birth of quantum physics. They were the pioneers who took the first courageous steps into a bizarre new territory. Planck's reluctant discovery of energy quanta, born from the ashes of the ultraviolet catastrophe, was the initial spark. Einstein fanned that spark into a flame by showing that light itself was quantized, giving us the photon, and Bohr used that flame to illuminate the inner workings of the atom, solving the puzzle of its stability. Their discoveries shattered the smooth, predictable world of classical physics and replaced it with a grainy, probabilistic one built on discrete steps and quantum leaps. They opened the door, but the journey was far from over. In the years that followed, a new generation of physicists like Schrödinger, Heisenberg, and Dirac would walk through that door and develop the full mathematical framework of quantum mechanics, a theory that would lead to lasers, computers, nuclear energy, and our entire digital world. It all started with a simple question about why things glow when they get hot, reminding us that the greatest revolutions in science often begin with the simplest curiosities. Thank you so much for joining me on this journey back to the birth of quantum physics. It's a mind-bending topic, but it's at the core of how we understand our universe. Coming next, we enter the quantum realm itself, a place where particles vanish and reappear, where light becomes both wave and matter, and where reality itself starts to break apart. Get ready for the quantum revolution and the realm beyond, the story of how science stepped into the impossible. Thank you for watching this video. Don't forget to hit that like and subscribe button. See you in part 2 of this video.